3, 2, 1. Hi, pre-cal students. It's me, Mrs. Fisher, and
Miss Willis.
we're coming at you from all different places. I'm at home, and obviously Miss Willis is at school. We are going to be teaching you today our Unit A, Day 4 lesson on recursive formulas. So recursive formulas are a subset of something we call sequences. And you last did this back in Math 1, and we know that that's a really long time ago. So we're going to first refresh your memory about what a sequence is. So at the very top, you've got a definition of what a sequence is. It is a function that has a domain of all positive integers. So the positive integers are the natural numbers. Those are the ones you learn to count. So 1, 2, 3, 4. Nothing negative, no decimals, not zero.
No, zero.
No zero, just the ones you learn to count with. And I don't think your parents taught you how to count starting with zero. So sequence notation then is also a little bit different. We name sequences using A sub n, and we use these little braces to go around the sequence because they're a set of numbers. Okay, so I want you to understand that when we name this, it's just like how we name a function. So a function, we use f of x, g of x, h of x. This is just like that, except we use the letters A, B, C, D, things like that. And we use a subset with the letter n because it's a natural number. When we use x's, it's because we can use decimals and negatives and things like that. So this kind of sets it aside and distinguishes it from functions because it can only be the natural numbers. So we name it slightly different, but just know that A sub n, B sub n, C sub n are just names.
Could we write it as like a parentheses in ever? Does it have to be a subscript?
It has to be a subscript for what we're doing here. You might see it written other ways in other textbooks or maybe on a standardized test or something like that. But the way that we're going to be writing them in this class is with subscripts.
Gotcha.
Okay. So the first type of sequence is what you did when you were in Math 1, and it was called an explicit function. So an explicit means straightforward. If I give you explicit directions to do something, it means I have given you straightforward instructions. If I say I've been very explicit with you, it means I have been very clear with you. So an explicitly defined function means it's very straightforward. So if you look at the definition here, it says an explicit formula defines what the nth term of a sequence is using the position of the term. So that might be a little confusing to you right now in terms of what that means. So we're going to give you an example. So in the first example, it says find the explicit formula for the sequence 1, 5, 9, 13, 17. And the dot, dot, dot means and so on. So it's going to continue on in this pattern. So my first question to you would be, what would be the next number in this pattern or in this sequence? So if we go 1, 5, 9, 13, 17, can you figure out what number would come next?
I don't know. I think I am adding 4 maybe. So
Okay, so what
1?
number will come next? So if you can figure out what number comes next in the pattern, that means that this is indeed going to be a sequence, and we should be able to write a formula for that. So an explicit formula means I want a formula that I can just plug a number into and get an answer. So number 1 here is the first term of the sequence. That should be the number I can get when I plug n equals 1 into a formula. The 9 would be the number that I could plug n equals 3 into and get 9 as a result. The 21 should be the sixth term in the sequence. So I should be able to plug in 6 into my formula and get 21 as the answer. That's how the explicit formula works. So now I need to come up with that rule.
So I would be able to find like the 21st term with this rule instead of writing it all out.
Yes, you should be able to find the 100th term in this instead of having to write out all 100 terms. So we are going to figure out what the rule is. So Miss Willis already mentioned for us that we're adding 4 every time. So if we're adding 4 every time, this is very familiar in terms of adding the same number every time. This is like a linear function. So with a linear function, that adding 4 every time is just like the slope of a line. So the idea is if we have the slope of the line being 4, increasing by 4 every time, one might think, oh, well, we add 4 every time. We know what the formula might be. But you have to remember it's like slope. So if you think like y equals mx plus b, like a line, that should be what our formula looks like. It should have the same general formula as a line. So if our slope is 4, our answer is going to have a 4n in it because we're increasing by 4 each time. So if I write a rule for this, I'm going to say a sub n equals, and I'm going to put my little braces, 4n, and then I need to think about how I can create those answers that are in this list right here.
By plugging in, what do we have to plug into the formula to get it?
So if I'm plugging in n equals 1 to get the first term, n equals 2 to get the second term, n equals 3 to get the third term, and so on, I need to make sure when I plug those n values into here that the result is going to give me 1, 5, 9, 13, 17, and 21.
Gotcha.
So right now that's not happening. If I substitute in n equals 1 right here, I do not get a result of 1. I get a result of 4. So remember, I said this should look like mx plus b. So I need something right here.
Has to equal 1. So what? 4 is going to be
4. So 4 times 1 is going to give you 4.
Subtract 3.
Yes, subtract 3 would give me a result of 1 right here. And then just double check and make sure that the rest of the pattern is going to hold true. So if n equals 2, are you going to get this 5 right here?
4 times 2 is 8. 8 minus 3 is 5. Yes.
Sweet. All right, so that would be your explicit formula. So the name of the formula is a sub n. The rule for the formula is 4n minus 3. Okay, so let's look at this next one. This next one's kind of tricky. So I wanted to show you a tricky one so you could kind of see what different kinds of patterns are out there. We've got 2, 5, 10, 17, 26, 37, 50. So with this one, this isn't really like the first one. The first one was going up by the same number every time. With this one, it's not really doing that same kind of thing. This one is going up by different numbers every time. So this one, you have to kind of think outside the box. Yeah. So this one,
my first thought is just, I don't think it's going to work. It's just too hard. I wonder what your thoughts are.
So my first question is always, can you figure out what number would come next? Because if you can, that means that this is a pattern.
I can. I think I can.
You think you can?
Yeah.
What number do you think comes next?
65.
Yes, 65 does come next. So if you can figure out what number comes next, that means that there is a pattern that exists here. Now, this one is a bit harder than others. So I just want to point out that an easier pattern is one less than everything that is written here. The pattern that's a little bit easier is 1, 4, 9, 16, 25, 36, 49, and 64. What do you notice about all those numbers, Miss Willis?
I feel like so if n is 1, 1 squared is 1. If n is 2, 2 squared is 4. It's like the squared version of the.
Yes, these are all squared numbers. So 1 squared is 1, 2 squared is 4, 3 squared. So the pattern is really n squared. And then the original numbers, 2, 5, 10, 17, and so on, are just one more than that. So you can have lots of different patterns. Some are a little bit more tricky than others. So let's take a look at number 3. Find the explicit formula for the sequence 3, 6, 9, 12, 15. So what's happening in this one?
Well, it looks kind of like I am multiplying something by 3, I thought, but then when I did, I think I'm on the right track, but it's not like 3 times 3. Like, I'm not taking the first term and doing that. But if I take the 1 and multiply, maybe.
Okay, it does start to look like you're multiplying by 3, but then what do you notice between each of these?
It doesn't work. Yeah, no. So I'm adding 3. I'm adding 3. Oh, I'm so dumb.
Oh my gosh, you're adding 3 every time. So again, this one is increasing by 3 each time. So if we're adding 3 each time, then this is like a linear pattern. So our slope is 3. And then we have to think about when n equals 1. When n equals 1, we want it to equal 3. And when n equals 2, we want it to equal 6. And when n equals 3, we want it to equal 9. Do we have to add or subtract anything from the 3n?
No, ma'am.
No, so that's it. Just 3n.
See, when I was saying multiply by 3, I was pulling from your previous problem. I was using those n values. I was like, I wonder how this 1 can be a 3. So I was like, oh, I'm timesing by 3. 2 times 3 is 6. 3 times 3 is 9. I didn't even put it back to adding 3 when I first did this problem.
Yeah, so you can also think about it that way.
Like, how do my n's make
You're
that?
so smart. All right. And now it's time to talk about recursive.
We are talking now about the recursive functions. So you probably also did learn about recursive functions in Math 1. We go over what they are. So this is not like an explicit function. You are able to plug and chug and get that thing. This one is just kind of telling us the pattern. So it tells you 2 pieces of information. It tells you your starting place, and then it tells you the rule for how to find the next termed based on the current now term. So the first example they've given us is that we are supposed to write the first 5 terms of the sequence. And they've given us, we have here a sub 1. Okay, I thought I had the slider. A sub 1. And then we are given the rule. So if they tell me my starting value, I know the starting value is 2, A1. I want to find the next one. What rule are they telling me to do to each of these numbers?
Add 1, because it says n plus 1.
No. So that's telling me the place value of the term. So the reason I know this is the first term is because in the n spot, they've told me n equals 1. So here, if I know n equals 1, I want the second term. So this would give me a2 equals 3 plus a1.
Wait, how did you get the 2?
Because I want to find, they've given me the first term, n equals 1, right? The next one we want is n equals 2. So the second, and that's just adding 1 to your n term. So if my n was 1, 1 plus 1 gives me the second.
Oh, I got it.
So
All
to
right.
get that second term, I'm going to take my,
Well, I do 3 plus 2 and I get 5.
yes. And then to get to the third term, so then it would be kind of the same thing. I would be doing a3. So that would be 2 plus 1 now because my n value is 2. Because this little n right here, n plus 1, we know equals 3. Okay. So to equal that, we are going to take the 3 that they've given us, but instead of adding a1, it's just an, which we know n plus 1 equals 3, so then my n value is 2.
Okay, so 3 plus 5?
Yes, so then I get
Uh,
8, and then I can keep going. Like, you can keep going by writing out all of that, like a4 equals 3 plus, now instead of a2, it would be a3, but you might start noticing what we are adding each time.
we're adding 3 like it literally says in the equation, because it literally says plus 3.
So easy. Add 3 and then add 3.
Oh, and that's all we
And
have to do?
that's all we have to do. The first 5 terms of the sequence. You just have to
Okay.
be able to read that sequence. That's the tricky part.
What if we're not good at reading?
I have office hours from 1 to 2.
Okay.
All right. Example 5. So we're going to find the first 5 terms. So now they've given us A1 and they've given us A2. I bet there's a reason. So they've given us 2 pieces of information, actually, more than we might need, or maybe it's we need them both. Thinking it's the latter of the 2.
That's too much.
Yeah, but instead of having to find 4 things, we only have to find 3 now. So the reason they've given us is if we look at this rule, instead of it saying n plus 1, it is saying n plus 2.
Oh, thank you for making that bigger.
You're very welcome. So here we know that my n value is 1, and here we know my n is 2. And so we want n is 3. So if we want n is 3, then this part has to equal 3. So a sub 3. If that is equal to 3, then what n value does it equal?
1?
Yeah, because 1 plus 2 is 3. So let's see. This is n plus 2. That's how I'm getting 3. So then that means n equals 1 really in the formula. So then this is a1 times n plus 1. So that's going to be a
2?
2 because n equals 1 in this right here. There's a lot of n equals. The way to think about this is a little tricky. Recursive can get real brain twisty because you have to figure out, like, really I'm finding the n equals third term, but when I'm plugging in my formula, the n is equaling 1. It's just a lot. So to get the third term, it's telling me I have to multiply a1 times a2, which equals 2 again. That's something. So let's figure out how to get the fourth term.
Do you just multiply? Because the rule said multiply.
Yes, I think we do. But what are we going to be multiplying together?
2 and 2.
Yes, because we are going to be, now that n plus 2 equals 4, my n value is 2, and n plus 1 is the third term. So 2 times 2 is 4. And then we're noticing we multiplied. So I don't have to write out the 5th term, but if you were to write out the 5th term, how you would get that, it would just be the 3rd term times
The 4th term.
4th term, which is going to give me 8. And that's all you gotta do.
Oh my gosh.
Yes. All right, let's do another guy. So a sub 1 equals 3, and this kind of looks the same. So they've told us a1, so the first term is 3, and the second term is 3. So we want to find the 3rd term. So now n plus 1, this equals 3 is what we want to find. So now we know that my n value is what? What is the n value of a equals, or the bottom equals 3? This n value here.
2.
Yes, because this tells me right there. So then if that's 2, then n minus 1 is going to be a sub
1.
because the n is 2 right there. All right, so that means I'm subtracting the 2nd term minus the 1st term to get the 3rd term. So this is the 2nd term and this is the 1st term, so that's going to be 0. And then I'm assuming all that means is I am going to be doing the 3rd term minus the 4th. Well, I like to sometimes just double check my mind. If this is 4, that means the n value is 3. So I get a3 minus a2. So the 3rd minus the 2nd.
So negative 3.
Yes. And then we keep going. The 3rd minus the 4th minus the 3rd. Negative 3 minus 0. Or
Are
0.
we going to show our work on this?
That's a good question. You know, with this virtual learning, it's a little tricky to show work. So I'm going to say no. But Miss Fisher might change her mind, even though she
I'm
asked.
going to ask a question.
I don't know. I'm always about showing work, but it's not 100% necessary to show you.
I don't think you need to on this. I'm going with no.
Okay. So, but now you've got me to show my work. It's going to be a4 minus a3, so the 4th minus the 3rd, so it's just going to be negative 3 again. All right, we only got one more.
Yes.
So, given the following sequence, this would be a good example right here to practice what Miss Fish taught at the beginning, finding an explicitly defined rule. So they've given us negative 3, 0, 3, 6, 9. Do we notice anything happening with that?
You're adding 3. Again.
So,
like we just did.
Exactly. So that's why you should see if you can write it, students, by pausing this video. So if we think about 3 as the slope, we know that the slope is written mx plus b. So we would say 3n. We would be multiplying by the slope to our n value. So if this is n equals 1 and this is n equals 2, we have to think, what would I be doing to this 3n to produce negative 3?
Subtract 6.
Ooh, I think that's right. Let's just double check with the 0. If I plugged in 2, I would get 6 minus 6, which is 0. Yes. Great.
Yes.
All right. Recursive now. So we haven't had to write a recursive, but it's super easy. So what we are going to do when we're writing this is you do have to state your 2 things. They want 2 things. So like in all the problems before, we have to state the starting term. So our starting term is represented by a sub 1. So a sub 1, and this one is the first term. So what's our a sub 1 going to equal?
Negative 3.
Yes. And then when we're writing the rule, so if we're trying to find the second, this is the first, we would say that n is 1. So we would take a sub to get the next term. You would just add 1 to the n value that you're using from that's already there, equals, well, we're taking that starting term. So this time it's going to be a sub n because we know we're using 1. So 1 would be my starting term. And then we're going to be adding something to it. What are we adding each time in this problem? We've already said it. We know we are adding
28.
That is wrong, Fish. My office hours are from 1 to 2. But yes, not 28, but adding 3. So
Yes, 3.